obviously causes a lot of trouble is the whole idea of entropy. It raises its head in various guises. I think it was, wasn't it von Neumann said on one occasion to somebody, oh, mention entropy because no one understands it, so you can get away with anything if you talk about entropy. Or words to that effect, in any case. I mean, that was the sentiment of what he said. Now, but there are a lot of other ideas which sort of go together, I think, here. And these are the things we started to look at. And that's why we said that we've... come on. We put these two talks together once again. Recently, there's a paper come out in Nature of some people purporting to have experimentally proved an assertion made by Landauer some years ago. I think it's an interesting thing that, as a sideline, that many years ago there was an article in the American journal Science, and I wrote a letter to Science criticizing this article. And before you could turn around, Science had published the letter together with the response from the original correspondence. So everything was out in the open. With Nature, that doesn't happen. With Nature, you have to write to the original correspondence, and they can say what they like. I'm not disparaging people in saying that, but they can literally say what they like.
Or they refuse to reply, and then nothing happens.
But in any case, nothing happens. Nature, as an aside, Miles, a small aside for you on this one, there was one occasion when Nature was forced to reply because the then editor, Maddox, made a load of trivial mistakes in his editorial, and myself and a friend wrote a letter tearing him to pieces, and Maddox didn't reply and didn't reply and didn't reply, and we took him to the Press Complaints Commission and they gave him 2 weeks to publish or else. So maybe that would be a nice little aside for you. So we started to, again to look at these things, and Landauer's suggestion, I've just put one or two things on the board. A number of them you'll be familiar with, so don't take it as an insult that I've put them up. I've just put them up as a sort of a guide for me chatting away, and in case there's something with which one or two of you aren't familiar. Landauer made this original suggestion that the erasure of information is basically a dissipative process, and therefore that a small quantity of heat is necessarily produced when a classical bit of information is deleted. Now, at first sight, you may think, well, you know, this is okay, what's wrong with this? But actually, it raises a large number of questions. Because Landauer, in coming to this conclusion, he actually argued that computing machines usually involve, I'm quoting again, devices which perform logical functions which do not have single-valued inverses. He then went on to claim that this logical irreversibility is related to physical irreversibility and requires heat generation for each, typically of the order of sort of K times T, to be associated for each irreversible function. Now, there are a number of questions that can be raised here, some of which we've raised before, and those of you that have purchased this, I trust, Richard, that they've purchased it already.
No, that's one left over.
Yes, I know, but I trust all the others have purchased before I say what I'm going to say.
Oh.
Because we talked about some of these points in a couple of articles which are in those proceedings, so you can check up on them. But one of the big things here is, and this is a thing that often puzzles students, is what do we really mean by a reversible process and by an irreversible process? It sounds trivial to us. It's exactly the same as when you're talking about information theory, and basically when you're talking about information theory, we all think of information as we think of it in everyday life, but that isn't what people like Shannon meant by information when they were coming up with their theories. And the same sort of thing is true of this idea of reversible and irreversible processes. Now, one idea that I put on the board is that reversible processes are really not processes, at all, but sequences of equilibrium states. That's one idea. The second, you could say that the real criterion for reversibility is that no changes of any kind must remain in the surroundings of the system when the given process is followed by the same process taken in the opposite sense. In other words, you are going around a complete cycle and getting back to your starting point. And when you get back to the starting point, everything is to be the same as when you started out. It's seemingly quite straightforward. But then, of course, another one is to say that a process which is irreversible must take place infinitely slowly. This is another thing that is stated. But of course, if you've got a process that's taking place infinitely slowly, it's not necessarily reversible, as is evidenced by this idea of a discharge of a condenser to a very high resistance. Now, these are seemingly trivial points, but they can lead to a lot of confusion. And it's interesting that in Landsberg's 1961 book on thermodynamics, when he's discussing the Carnot cycle, he doesn't talk about reversible processes at all. What Landsberg actually does is go through the Carnot cycle in the forward direction and go through the Carnot cycle separately in the reverse direction. And so he gets over the problem of talking about reversibility and irreversibility. The other thing that I think is interesting about that book, and maybe is a word of warning to all of us, is that bits like this, something like this comes into the book somewhere. Bits like this don't appear in the actual book. They actually appear in the examples at the end of the chapters. And with all the examples, we'll have an example, and then in brackets afterwards will be hints for solution. And some of the hints for solution are actually the solutions. And so, what?
Would you please enlarge this somehow? Because for people in the
Try view, John.
Right.
What's it, view? View. Just try that. Let's see.
100%.
Yeah, 100%.
Oh, yes.
100% box increase.
This actually.
Put on 200 and then cycle it back to 150.
This actually.
Oh, yeah, why not go down here?
So you get over here.
No, this was that one. Text.
Up to about 148.
Text width, does it?
Yeah.
Does it?
Yes, it takes maximum text width.
Okay. Oh, yes. Yes. Okay. And then. Okay.
Is that an
That's
impact?
better.
Sorry about that. No, that's okay. Just that I'm useless with computers, as you all realise by now, I hope. I said to Guy earlier, if there's a panic, I'll scream for him, just as I scream for my son when I'm at home, if anything goes wrong. So, so you've got this this problem arising with thermodynamics all the way through. And as I said, lots of these things in Landsberg's book appear in the examples at the end of chapters. And you are left wondering, in retrospect, if this was a way of introducing some, what might be regarded as provocative ideas, without being in the main text, and therefore not subject immediately to an immense amount of criticism, possibly, which I know Landauer did experience quite a bit of criticism for some ideas from certain people over the years, and maybe it was to obviate that sort of thing. But once we come to look at thermodynamics, forget everything else for the moment. Once we come to look at thermodynamics, with what are we really concerned? When you go back to the origins of thermodynamics, what you're really looking at are processes which somehow or other involve heat. So, I'm not, as I said before, I'm not wishing to insult you by putting these up. It's just that I wish to draw your attention to a number of points. When you go back to the beginnings of thermodynamics, all right, you can go back to Carnot, but you come forward a little bit from Carnot, and you find that the subject is modernized, not quite as we know it now, but it's modernized with the wording of things to a certain extent, and we ended up with two versions of the so-called famous second law. And the ones that the wording of them that's usually published there is the one due to Thomson and the one due to Clausius. And the crucial thing about these two statements of the second law is that they're saying that something is impossible, but in both instances they state quite specifically that there's some reaction is impossible when you look at a cyclic process and in the absence of other effects. Both occasions. Using these two forms, or one or other of these forms of the second law, you can deduce this quite famous equation up at the top. And what that equation, never mind what it says when you look at it, what you actually start out by doing is looking at a small increment of heat being given to a system or taken from a system. And the little dash indicates that mathematically that quantity of heat mathematically is an inexact differential. And the second law tells you that you can find an integrating factor, which is 1 over the absolute temperature T. And so the d dash q over T is now an exact differential. So that if you want to integrate, you can integrate without any trouble at all. And you call that, in thermodynamics, ds, which we say is the change in entropy. Now that is how it comes about in thermodynamics, and whatever else you say about it, that quantity ds, whatever it is physically, and I'll be quite honest with you, don't ask me because I haven't got a clue, but whatever that is physically, it is irrevocably linked with a change in heat in your particular system. But round about the same time as you were having all these developments due to people like Thomson, you were also having the development of statistical mechanics. I suppose the origins of it are always linked with the name of Boltzmann. And the reason, of course, for this is that you're wanting to look at assemblies of large numbers of particles. And you can't when you've got a very large system, you can't very easily write down the exact equation of motion of each individual particle. And even if you could, you'd have such a huge list of them, there's no way you would be able to solve that collection of simultaneous equations. So what they did was to adopt statistical techniques. It's a pity, but when they did this, it was done independently. It was sort of physicists working at it. And many years later, they start to talk about a link between so-called statistical mechanics and information theory. And as Bernard Landauer in Italy, as he said on numerous occasions, it seems to him, looking back, that it's a great pity that statistical mechanics and information theory didn't develop together. It could have saved a lot of time, and it could also save a lot of confusion. For example, in statistical mechanics at present, you've got various expressions for the entropy. We normally think of the one due to Boltzmann, the one that's engraved on his tombstone, the entropy of statistical mechanics. The actual entropy now, not the change in, always written as K log W. But of course, there are other expressions for entropy around, and what was it, at the end of the last century, this, well, I'm not sure what he is, because I think he was born in Greece, but then he ended up in one of the South American countries. This man called Salles came up with a new form of the entropy, which he claims, he almost came to him in a vision. And there's this quite complicated expression. And what nobody noticed, and the comment that nobody will publish, is that the expression that Salles came up with had been known for years and years and years to people working in information theory. It went back to something like the 1920s, I've got the exact date, that this, or a form of this expression had been known. And we've got a lot of stuff going on with one group working independently from another group. And this can, and in fact has, in my view, led to quite a bit of of confusion, and it's certainly leading to a lot of confusion among students, because what we're actually having now is that people start to develop statistical mechanics, and after a point they say, oh, we want to work out, let's say, the internal energy of a system by using statistical mechanics measures. They do it. Or we want to work out the pressure. They do it. So they then go on working out these various quantities, and then they want to work out an expression for the entropy. Now, very often, the expression for the entropy is worked out by going back to the so-called Euler relation that you get in statistical mechanics. In other words, that the entropy is equal to 1 over the absolute temperature multiplied by U plus PV minus mu n, where n is the total number of particles. And that is an expression which comes out of pure thermodynamics. It incidentally comes out of thermodynamics, which is applicable only to so-called extensive systems. In other words, systems in which various quantities are additive. The internal energy is additive, the volume is additive, the number of particles is additive. And when you go through, in fact, in ordinary thermodynamics, to derive that equation, to find the integrating factor of the d dash q, you actually have to make a basic assumption, or let me reword that. You normally make the basic assumption that q, the quantity of heat, is an additive quantity. Now, I changed my wording there because you can actually get around that, and you can assume that Q is not additive and still derive that equation. But basically, the equation that appears in all the books, the derivations, you assume Q is additive, and therefore you've got that the S is actually additive as well. This is hidden away once again. But of course, going along this path in statistical mechanics, making use of thermodynamic results means that people then go on and assume that a quantity that you derived in statistical mechanics is the same, in effect, as the quantity that you derived in thermodynamics. But thermodynamics is a purely macroscopic subject. You're dealing there with, let's say, the internal energy, which is a quantity of energy. Once you go across into statistical mechanics, the U, the internal energy you're looking at, is a mean value. It is a quantity which can, in fact, fluctuate. And if you go to, you can look through the literature and find that there are loads and loads of papers on fluctuations in thermodynamics. But those fluctuations are in what I think you should more properly call the subject statistical thermodynamics, where some statistics is coming in, because in straightforward thermodynamics, you've got purely macroscopic quantities, and you're not going to have fluctuations actually coming into them. Excuse my looking down occasionally at these notes, and you'll gather that I'm not very happy looking down at notes all the time, but I think it's a good idea if I do just occasionally just keep myself vaguely on track in any case. But I'm not going through the article, I'm not going through it. This is just meant to be an introduction to some of the ideas that David and I have been pondering over for quite a long while. And I think you can see already that if you've got some research undergraduates, and contrary to popular opinion in some circles, there are some of these discerning undergraduates around, this can cause them problems. Yes, the brighter ones will quite ruthlessly accept something, learn it off by heart, and churn it out in an exam in order to get the high mark. But they're there with the questions at the back, and some of them can find some of these ideas quite disconcerting. And what is the link between the two? Well, as I say, to all intents and purposes, when you come to thermodynamics and statistical mechanics, the link is basically a big assumption, which may be true, but it's still an assumption. Now, of course, you go on a few years, and you start to have the build-up of information theory. Yes, it had been going on since before statistical mechanics was born, to a certain extent. But it really grew and came more to the public, more to the fore as far as the public is concerned, possibly with the publication of works like that of Shannon and so on. And lo and behold, you find in information theory, you again find a quantity called the entropy. And you again find that it has this similar form to the form that this form that Boltzmann had proposed. With slight differences, but basically of the same form. And so there's this tendency to say that that is exactly the same. Now, if I can find the quote, yes. Brillouin wrote I think rather good readable book, Science and Information Theory. But it's a very interesting book to go through, because you find that the first 8 chapters are devoted solely to a build-up of information theory. And then suddenly, at the beginning of chapter 9, we find him stating the following. A close connection has been discovered between information theory and thermodynamics. Information appears related to entropy. Well, it's nice to see the word appears coming in there. But the first part of that statement, there's no basis for that statement anywhere at all. No real basis. And yet, here we have it being stated. And what is more, accepted. And that, of course, is what is behind this whole business with Landauer. Just scan it back down, because this is the with Landauer's suggestion. This supposed link-up, this supposed idea that this quantity entropy, which appears in thermodynamics and in statistical mechanics and in information theory, that in each of those 3 seemingly separate disciplines, entropy represents the same thing to all intents and purposes. Well, this obviously raises an absolutely massive question, because you really do have to ask, does it represent exactly the same thing? The word information, again, Brillouin explains that Shannon, by information, well, Brillouin suggests that use of the word information is probably an unfortunate piece of terminology, because Shannon, in his ideas, was interested in a mathematical theory of communication. He wasn't interested in information as we understand it in everyday life. He was more interested with information as being the basis of the probability that a particular character would be received based on the properties of the alphabet, which is not quite the same thing as we normally understand by information. Yes, in very specialized circles, it would be understood by that, I agree, but not necessarily, certainly not by the man in the street, so to speak. So, what is the basis here for all this? Well, basically, with information theory, you get the idea that a bit of information is represented by a constant times log 2. The constant is usually put equal to Boltzmann's constant, and then they say if you multiply that by capital T, you've got a quantity which has the dimensions of energy, which is fine, that's quite correct. But the idea of linking it in with thermodynamics comes from then going back to ds equals d dash q over t. And if you're saying this is a quantity which multiplied by t, it's a quantity of heat, you are bringing in some basic macroscopic thermodynamics. And this is where the idea of this quantity of heat as suggested by Landauer, comes in. When you come to the actual paper discussing an experiment to validate this, one of the big problems that you come across immediately is that, in my view, the statements of the second law which we should stick with are those due to Thomson or Kelvin and Clausius, where we're talking about a macroscopic process taking place in a cycle, in a complete cycle, in the absence of other effects. I know that it's in vogue to pick up loads of papers and books these days saying, oh, the statement of the second law is that entropy cannot decrease. Blanket statement. I ask you to pause for just a second and think about that statement, because little pause and you'll realize that it's a load of rubbish. You have your statement of your second law, in thermodynamics that is, and you know that you can give the system heat, you can take heat out of the system. And so the usual way in which we operate things, it means that we'll regard a quantity of heat given to a system as, let's say, positive, and a quantity of heat taken away from a system, let's say, negative. And so if you've got a dq which is positive, ds is positive. If you've got a dq which is negative, ds is negative. And you're going to have negative changes in entropy if you go around a Carnot cycle, because when you go around a Carnot cycle, you get to the end of it, you're back where you started. Nothing has changed. And one of the crucial points that is made in the discussion of the Carnot cycle is that the entropy is the same when you get back to your starting point. Now there is one possible get-out here, and I know it's a favourite comment of David Sands, or favourite query of David Sands, and that is, but is this quantity, the entropy, is it actually a state variable? Because there is a tacit assumption that it is in virtually everything. There is some, how shall I put it, computationally experimental evidence to suggest that it may not be. If that's the case, there are more big questions to be asked about thermodynamics. But the crucial thing here is, of course, that with the experiment supposedly validating Landauer, it's not absolutely clear that you've got thermodynamic cycles being described. It's exactly the same as that work that came out a few years ago by a big group of Australians. One was a man called Evans, and he had this group, and they purportedly proved that the second law was being violated. And they pulled a very neat little ploy, because they got E.G.D. Cohen on board with them. And so having a nice big name on board in the field of statistical mechanics gave credence to everything. And they were saying this, the second law is violated because we produced this example where entropy does not increase. But they didn't have a cycle for a start. There was no cycle involved. They were just looking at a particular reaction. Well, as I've said, obviously, you can have your entropy decreasing. That doesn't violate that equation at all. And there's no reason to suppose that it does. The idea of entropy increase is another of these ideas that, yes, will have a degree of validity in it. But what we need to be looking at is what is the degree of validity of that claim. And this is the same with a number of the basic factors that come into basic thermodynamics, I would put to you. But if I may, ladies and gentlemen, I'd like to stop at that point and hand you over to my colleague, David Sands. And if anybody wants to lynch me, I'll be sitting at the back next to Richard Amoroso. But thank you, ladies and gentlemen.